Good morning, and welcome back to the next TMA Blue Tech panel on marine hydrokinetics, or as we like to say, marine energy. My name is Jason Bush, Executive Director of the Pacific Ocean Energy Trust, poet, and it's my honor today to be able to participate in all the panels and host a roundtable at the end of the day. I want to remind folks at the end of the scheduled panels today, we're going to immediately go into a roundtable event. And we encourage all the panelists and moderators to join us at the end of the event. And we hope the audience, of course, will join us as well to hear some final observations regarding the future of clean energy from the oceans. With that, I want to thank again Michael Jones and Matt Klassen and all the team at Maritime Alliance for bringing us all together today for this informative event. Our next panel is going to discuss marine energy, and we've got Matt Sanders is going to moderate for us. I've known Matt now for over a decade. He works with me at the Pacific Ocean Energy Trust, but I'll read a standard bio for you instead of telling you personal stories about him. So Matt is the program director for the Pacific Ocean Energy Trust, a 501c3 nonprofit with the mission to promote ocean-based climate solutions. Matt is the marine energy lead for POET and is currently leading POET's effort as the network director for the testing expertise and access for marine energy research, as we call the TEAMER program. Matt earned his Bachelor of Science in Forest Sciences from Colorado State University and his MBA from Portland State University. With that, I'll hand it over to Matt Sanders.
Thanks, Jason. Thanks to TMA Blue Tech for having us back this year. Speak again. Really excited to present this panel today and moderate it. Really great opportunities and a lot of updates and exciting things happening in the marine energy world today. Specifically today, I think most of this panel will be talking about wave energy devices, but marine energy does encompass both tidal and ocean currents, as well as other types of marine-based energy conversions. Just real briefly, I want to take about 30 seconds to talk about the testing expertise and access to marine energy research program. It's an opportunity that POET is administering, supported by the U.S. Department of Energy, to provide access to marine energy developers. That includes both wave and tidal and any type of current energy. Access to testing and testing infrastructure in the United States, as well as expertise at national labs and other institutions around the country. So I recommend anyone following this who might be a technology developer looking to access the world-class expertise we have in the United States to check out teamer-us.org. And I'm actually the program director for the Pacific Ocean Energy Trust, not the Oregon Wave Energy Trust. That was our former name. So feel free to check us out at pacificoceanenergy.org for all the great work that POET's doing as well. With that, I'm happy to hand it off to Jack. Jack will start the panel. I'll let everyone on the panel do their own intros. So feel free, guys, to talk about yourself for a few minutes before you start talking about the technology. With that, Jack, go ahead. Thanks.
Great. Thanks so much, Matt and Jason, and thanks for having me here. So I know a lot of my fellow panelists are in the grid scale wave energy, but I will start off by talking about small scale ocean wave energy and its utilities for ocean science. Next slide. So I'm with a startup company called Ocean Motion Technologies. We are fabricating a small-scale off-grid modular ocean wave energy device, and most of our commercial partners focus on low-power applications in data buoys for ocean observation, maritime monitoring, offshore aquaculture monitoring, and surveillance for coastal security and defense. And this device is controlled by a artificial intelligence system, so it can adapt to ambient wave conditions and optimize power output. And personally, I am trained. I was trained as an oceanographer, and currently I am also a research fellow at NASA's Jet Propulsion Laboratory. So for this presentation, I'd like to talk about small-scale marine hydrokinetic energy and echoing one of the major topics here at 2021 Blue Tech Week, which is the interconnection between the space industry and the blue economy. Next slide. So this is just some background illustrating how the two industries, which are seemingly different, but are actually quite interconnected. So in 1978, NASA launched the coastal zone color scanner on board of the Nimbus 7 satellite, and this is one of the first surveillance ocean observing satellite launched into orbit. And CZCS is a multi-channel passive radiometer, and it records quite literally the color of the ocean. And because it's a spaceborne platform, it offers unprecedented spatial and temporal data coverage of the entire ocean surface that was never seen before in the field of ocean science. And the first few years of satellite oceanography generated lots of literatures like this one you see on the slide, where these groundbreaking ocean color data sets proved or disproved many of the theories in oceanography and allowed researchers to see very large scale currents and other features like never before. Next slide. And since CZCS, NASA and space agencies from other nations have launched a lot more ocean observing satellites, and they have been providing a huge amount of data over the last 20 years. Next slide. So just to help everyone better understand how space research is deeply connected with ocean science, we need to get into the weeds of this field, and this is just one of the many examples and something I work with every day. So the bottom right of this slide is showing marine phytoplankton, and these are single-cell plant organisms that are ubiquitous in the ocean surface, and they are just like plants on land, so they do photosynthesis. And all of us are alive because of these tiny phytoplankton in the ocean. And just like plants on land, they have the chlorophyll pigment, which can be directly measured optically by satellites. So this means we can very accurately quantify how much plant biomass is in the ocean, but from space. Next slide. And if these data are compiled over time, you can see the seasonal time series over the entire globe. And you can also see these very large scale features on a decadal scale. Next slide. However, this very powerful technique has its own limitations. And that is remote sensing data usually requires very rigorous calibration and validation. And this is more difficult to do in the ocean. And sometimes when coastal oceanographers want to observe the near shore, satellite remote sensing just doesn't always have the necessary resolution to resolve these features. And passive sensors like the one I just mentioned earlier for observing chlorophyll are also highly dependent on ancillary environmental factors like cloud cover or light availability. And so in the top panel, you can see the 2020 chlorophyll time series from the Western Antarctic Peninsula, which is lacking about 6 months of data, and this is mostly due to the polar nights. And on the bottom panel, this is actually our debut of an experimental algorithm that we're working on, which can detect glacial meltwater fraction. And we're very interested in the time period of December 2015 because it corresponds with our field work in this area. And you can see the image is lacking data, particularly in the southern part, and this is due to light availability and sea ice. So we really need cost-effective big data solutions in the ocean to close these data gaps. Next slide. And we're really lucky because the blue economy is transitioning to a big data paradigm, and these big data capabilities can be achieved by 3 categories of technologies. First is autonomy, driven by cheaper and more reliable autonomous technologies. And we see a lot of vendors working on this category right here at Blue Tech Week. It's also driven by network, which refers to linking these autonomous sensors and platforms over space and in time so they can communicate with one another. But there is a R&D bottleneck in realizing this big data paradigm. And the problem is not autonomy and network, which we have basically perfected on land. The problem is we don't have cost-effective power solution to support these big data infrastructures. So this makes big data really expensive in the ocean. Next slide. And let me just quickly clarify what I mean by big data, and this is quite literally what end users work with. So when end users demand big data, we're talking about higher data resolution, meaning more rows of data. So we have to sample faster at more locations. We're asking for more variables, meaning more columns of this data. So this is usually achieved by installing more sensors or doing feature engineering. And in applied ocean sciences, we're also asking for near real-time or live reporting, so transmitting a copy of this data frame almost instantaneously. And satisfying these capabilities would gradually shift the blue economy and ocean science to a big data paradigm. Next slide. And circling back to the interconnection between the space and ocean industries, this reminds me of the commercialization of CubeSats over a decade ago. And the development of CubeSats were driven by major advances in cheaper and more reliable sensors. There was also a huge demand for big data from space. And these CubeSats have many very clear competitive advantages, and they can supplement or sometimes completely replace conventional spaceborne observation systems. But there was a very slow adoption by the industry. And what I just described to you is exactly what small-scale ocean energy is experiencing today. But the difference here is that the vendors in the space industry back then did not have the equivalent of the DOE, POET, and TMA to advocate for their community at a high level. So our community has a major competitive advantage in contrast to the space industry. And all we have to do is to figure out ways to engage more end users and also find ways to collaborate with one another in order to meaningfully support this paradigm shift to big data in the blue economy. Next slide. And that's all I have. Thanks.
Jack, thank you very much. Very informative and interesting presentation there. Really neat to see it in person here. I've been following you guys for a bit. I think we're going to go next to Rens. So Rens, please go ahead.
Great, thanks. Hi, everyone. Rens Leesman, CEO of Sea-Power. Thanks to Matt, thanks to Blue Tech Week for the opportunity to speak with you today. So a little bit of background about Sea-Power. Sea-Power is an ocean energy power and data company. Our product development and delivery team is based in Oregon. Actually, our original technology came out of Oregon State University. I'm based on the East Coast, and we also have UK operations. So since the company was formed, we put tens of thousands of hours into the engineering, manufacturing, testing of our systems. That's resulted in a first product actually being sold and starting to build a commercial pipeline as we release our products into the market. We've brought in 50 patents to date in 3 families. Actually just filed a new provisional yesterday on the product that we're going to focus on today. So next slide, please. I want to frame the discussion a bit, and I find this to really be an amazing stat. 35 billion versus 10,000 sensors, IoT sensors, really Internet of Ocean Things. And what I think this shows is really just how far behind the ocean economy is with regards to the terrestrial economy. So if you think about all of those macro trends, decarbonization, autonomy, AI, robotics, electrification, all of those macro trends that have dominated the terrestrial economy, they are just slow to come to the ocean. And I think Jack touched on this in a second, but it begs the question is, why is this? Next slide, please. It's really because the ocean, it's a power desert, I think, as we like to refer to it. And I'm preaching to the choir here, but really any time that you want to do anything in the ocean, you have to take people and power on site to get it done. And what that means is doing any operation, it's costly, it's carbon intensive, it's complex. So at Sea-Power, we solve this problem by turning that power desert into an energized, data-enriched environment. Next slide, please. We're bringing 3 products to market: ocean energy products, ocean energy and data products. And we fit roughly into this gap. We call it a 10 to 10 gap, roughly 10 watts to 10 megawatts. It's not a perfect division, but it gives you an idea. And this is really the largest market sector for power and data at sea. And this gap is created because of solar's inability on the lower end to cover the power spectrum, the power range here, and offshore wind, its inability to scale down and cover some of these areas. And the ability of these systems to provide power and data at sea is very significant, and with a significant value proposition, some 50 to 90% reduction in cost and emissions. Now, we're going to focus on the Sea Ray today. That's a part of a class of systems called autonomous offshore power systems, or AOPSs. And you can think of an AOPS as the combination of a cell tower and a data server and a charging station, but out in the ocean. Next slide, please. So the purpose of an AOPS is to provide power generation, local energy storage, data services, and connectedness. And that is at its essence. And the goal here is to provide power and data support for a variety of mobile and static assets, whether it's on the surface or on the seafloor. Again, many of the things that Jack was showing in his OV1 slide there. Next slide, please. So the primary use or the primary applications for an AOPS, Sea Ray, or anyone else's is to cover 4 essential use cases. And these are use cases that are really independent of the business model and industry sector. It can be commercial, defense, security, research, aquaculture. Because again, at its core, it's the provision of those power, data, energy storage, and connectedness services. So marine robotics, we have data gathering and communication systems, operating equipment, and then at-sea charging of unmanned surface vessels. Next slide, please. So the Sea Ray AOPS is based of sort of 3 essential components. The wave energy converter on the surface. For our system, we use a single line for station keeping, power and data transfer. It has copper in it for the power, fiber optics in for bidirectional high bandwidth transmission between the surface and the seafloor. And then a seafloor base unit, which serves as the gravity anchor, energy storage, payload interfaces. Now, the energy storage can be really scattered at the surface within the wave energy converter, at the seafloor, or a combination thereof. The Sea Ray does not have to be a moored system. It's also drifting. In fact, the first one that we sold into a Navy project is specifically a drifting system, and I'll show a picture of that in just a second. So next slide, please. And as I mentioned, the goal of any AOPS, and the Sea Ray in particular, is to be able to support a variety of assets, mobile and static both. And this can be AUVs, it can be static seafloor data gathering systems, it can be surface systems, operating equipment, tethered ROVs. It's really, the system is built, it's designed, any AOPS is designed to be agnostic really to the use. I've just shown some of the partners, customers that we have started to gain here over the last year as we get ready to release this system. Next slide, please. So we have an upcoming demonstration in Hawaii at the WETS, the Wave Energy Test Site, the Navy's test site. This is a DOE and Navy-sponsored project along with Sea Power. From the Navy's perspective, this application demonstration is also part of Coastal Trident 2021 and expect or hope to be part of Coastal Trident 2022 also. This is a 2 kilowatt system, generation capacity system. We have 55 kilowatt hours of energy storage on the bottom. Again, as I mentioned, bidirectional data and comms. This system has been designed to survive the 100-year storm off the Pacific Northwest coast. We're getting pushed to think about survivability in 500-year storm conditions, but not quite there yet. It's built to meet market needs for non-complex logistics. This system's going to get deployed in Hawaii with an 85-foot workboat. I think it has 4 crew members on board. And it's a very small, it's containerizable. It will ship to Hawaii in a container. Its total mass is 15 tons. Next slide, please. So just to give you an idea of what we are demonstrating in Hawaii, we have a Saab Sabertooth that'll be operating in untethered mode. I've listed the variety of sensors that it'll have on board. It'll be performing bottom surveys, change detection, mine countermeasure type operations. We have an environmental monitoring system from Biosonics. This is effectively ultrasound for the surface and the water column to see what's moving, whether it's mammals, fish, swimmers, or surface vessels. We're approving for oil and gas application, methane leak detection asset. Fugro will be putting a seafloor data gathering system in, and we'll be supporting multiple of these assets simultaneously. It's really be the first time that anyone has done that. We have a new OEM that's going to come in with a subsea control module and a video surveillance system also. Next slide, please. Just real quick, this is a picture of the nacelle of the Sea Ray, the K2 at NREL for validation testing. It's there. We'll be shipping out soon, hopefully. Next slide, please. This is the K2, or sorry, the K.5 that we sold. This is going to that Navy project that's come out of the paint shop. And just to give you an idea of scale, that system is roughly about 8 feet across. So again, light, compact, portable, easily deployable. Next slide, please. So with that, I'll close. Thank you very much, and look forward to any Q&A afterwards. Back to you, Matt.
Thanks, Ernst. Before we get to Patrick, I believe Patrick's next. Yeah, just want to encourage anyone in the audience today to start putting some questions in the Q&A feature on the Whova app there, and we'll make sure to address those at the end of the session as well. So with that, we'll go from sea power to core power. Try not to confuse those. Two very different technologies supporting a similar market. But Patrick, go ahead. Look forward to your presentation.
Thanks a lot. My name is Patrick Mahler. I'm CEO and co-founder of Core Power Ocean here. And we are a developer of a new type of high efficiency wave energy technology. Next one, please. So Core Power, we are headquartered in Sweden with operations in a few places in Europe today, and we hope to keep growing in California and Oregon in the coming years here. We stand out a bit about having followed a very structured product verification approach from day one. So we're currently in stage 4 with our first commercial scale system. So today we're a team of 65 people with 14 nationalities, and we've secured funding to bring bankable wave technology to market all the way. Next one, please. And of course, the opportunity that we are working to unlock, it's the huge wave energy opportunity, the largest untapped source of clean energy out there, about the same capacity that is the opportunity here as all the nuclear of the world or all the hydro of the world today. And what we find as the most attractive part with wave energy is not just the size of the opportunity, but also here the complementarity and the consistent production profile of wave energy, where it can become a key tool to fill in the gaps when it's not windy and sunny and future electricity systems, and thereby accelerate the transition to 100% renewables. If we take the next slide, we can see an example from California. This is a simulation we've done with weather data from 2018, actual production of a week in October of wind, the light blue, and solar, the yellow, where we used wave buoys along the Californian coast to simulate as if we had 6 gigawatts of wave installed. And it's very interesting. What you can see is that the wave energy profile is very consistent. It's much more flat, and it's also much more predictable compared to wind and solar. And you can see when the wind goes down, there is very little correlation to the wave profile here. And you can use wave energy as a complement to fill in the gaps and make a much more steady energy system. If we take the next one and have a look at the annual profile for California and Oregon, it becomes extremely interesting. To reach 100% renewables, you have both wind and solar peaking in the summer, and you would then have a gap in the winters. Here, wave energy comes in with a anti-correlated profile. So adding the right mix of wave, wind, and solar makes it possible to pretty much perfectly balance supply to demand over the year, which takes care of seasonal balancing which is an amazing tool, a lot more efficient than long-term storage if you can balance it already at the generation stage. So if we take a look at the next one, we've participated in a number of energy system studies where wave energy has been included into the mix. And in each study we've been part of, it's found that the complementary production profile here of wave energy, it just allows a smaller system to reach 100% renewables. So you can have less total generation capacity, less storage, and less grid, while still balancing supply to demand. And that is really the big role of wave energy. So we should use the ocean here, the Pacific, as a huge energy storage unit to accelerate the transition to 100% renewables. So next one, please. Looking more into the challenge of wave energy, one more, please. I mean, historically, wave devices, they have either broken in storms or they've just not produced enough compared to the size and the cost, and thereby the business models haven't worked. We've been working hard to address that, and we've radically changed that picture. If we take the next slide, please. And we've introduced a new type of high-efficiency wave energy converters. One more, please. And this is our recent C3 device, which was our half-scale machine that we demonstrated in EMEC in Orkney. And in wave energy, we've proven new solutions. The first one is, next slide, please. Survivability in storms. Our devices are designed so that they are naturally transparent to ocean waves. They don't react to waves unless we actively control the devices. So in storm conditions, we use this natural state to protect us from storms and thereby get very good survivability. If we take the next slide, in regular sea states, we used advanced control technology that puts the devices into optimal timing with each incoming wave. And that strongly amplifies the motion and thereby the power capture. So we can deliver a large amount of energy compared to the size and the cost of the devices. So if we take the next, in average, we can get to, and here, this is based on research about 40 years from NTNU in Trondheim. Our lead scientist, Jürgen Hals, he did his PhD work together with Professor Fallness. And the phase control technology that they have introduced just changes the picture for wave energy. If you look at the next slide, in energy per ton, we can get more than 10 megawatt hours per ton of equipment out, which puts wave energy just in line with the best offshore wind technology today, actually a little bit higher structural efficiency than most floating wind concepts. So really improving the competitiveness. So getting a large amount of energy per ton makes it possible to reduce the capex, and then small lightweight devices makes it possible to transport, install, and service with low-cost vessels and port facilities, really bringing down the OPEX. So that contributes to a very competitive cost of energy curve with that. Next one, please. And we are currently in our stage 4 demonstration, so we are bringing our first commercial scale machine into the water next year. And after that, we're going to bring 3 more full-scale devices into our stage 5 array in the Highway 5 demonstration project, clock at least 8,000 hours of operation, and then achieve type certification from DNV-GL. With that, we should be ready to start shipping product in volume to customers by 2025 timeframe. So if we look into the current stage 4 demonstration on the next slide, please. We are doing this together with EDP and Wavec in Portugal. Here we're putting in a first C4 device in Q1, Q2 next year. And this is connected to the Portuguese grid through the Aguçadora substation, same place where Principal Power brought the WindFlow technology to market. And then we're going to add on 3 more of the C5 devices here in 2024, and also demonstrating a floating collection hub. If we take the next one, currently with our C4 machine, we built it in our machine halls in Stockholm. This is how the drivetrain looks like in full scale on the C4. And next one, please. We have invested in the world's largest dry test facility where we use simulated wave loading to debug and stabilize the equipment in a very stringent test program before we bring the devices into the ocean. And that's where we're currently operating the machine. If you hear some strange noise, I'm here in our offices with the machine hall just behind me, and it's like 2 big long-distance trains of capacity running back and forth, 7.2 megawatts of test capacity on this rig. Next, please. In Portugal, we built out a mobile factory concept where we're fabricating the composite hulls, the buoys themselves. And this, in the future, will be shipping the mobile factories from customer site to customer site, producing the hulls locally. If we take the next slide, we see how it looks in full scale. We use an additive manufacturing technology called filament winding, and we've invested in our own manufacturing cells to fully industrialize and show industrial supply chain capacity to deliver this at scale. So next one, please. We are a turnkey supplier of the full farm infrastructure, and we're designing these devices to be compatible with a typical offshore wind infrastructure. So you can co-locate wave arrays together with floating wind, as you see in this picture, using the same electrical infrastructure and selling electricity, which is much more consistent and thereby having a higher value in future markets. Next one, please. One of the projects where this is being developed is developed by Simply Blue Energy that we heard also speaking on the previous session in floating wind. Their Saoirse project on the west coast of Ireland is a stepping stone project for wave energy and is developed as a commercial project of 5 plus 30 megawatts of capacity to start with. And we hope to see devices there in the water starting the construction in 2024. Next one, please. We are looking at ocean energy as a huge opportunity here to build local industry. For California and Oregon, it's an amazing opportunity that we really hope to be part of driving. In Europe, if we take the next slide, we're seeing quite a lot of commitments right now. The European Commission has put targets to have 100 megawatts operational in the water by 2025. That's wave and tidal combined. And then to have a gigawatt installed by 2030 and 40 gigawatts by 2050. From Ocean Energy Europe, the branch organization, we think it should be 100 gigawatts by 2050, but we're happy to have 40 so far as clear targets. And we hope to see similar commitments made for California and Oregon. We hope that California Energy Commission can put wave energy on the roadmaps, put it into the renewable portfolio standard, and really drive the adoption and take advantage of the huge local industry and job creation opportunities that this brings as well. Thanks a lot. Next slide is my final one, I should say. Thanks.
Great, Patrick, thank you very much for very interesting perspective on the utility scale and in the European market as well. Look forward to some questions later on. I also noticed you guys might be at Ocean Energy in a few weeks. Hope to see you there. I might be there myself if COVID doesn't shut me down before that. Let's finish with Marcus now. Marcus Lehman from CalWave. Marcus, the floor is yours, and then we'll go to Q&A after that. If anyone has any questions, feel free to write them in the Q&A section at this time. Thanks.
Thanks for the intro, Matt. This is Marcus from CalWave Power Technologies, co-founder, CEO. Next slide. Yeah, today I want to speak a little about our pilot in California, starting off with kind of our general philosophy. And the fundamental challenge of wave power is really that large gap. As we've heard before, survivability is key for infrastructure assets that go out for 20 years. And we have to design for the 50-year return wave. And as we can see, that doesn't actually contribute a lot to energy production. And that's been really driving our thinking since the beginning, coming out of Berkeley Mechanical Engineering back in 2012. Next slide, please. And so similar to our modern wind turbine, just on a very abstract level, we can identify 4 major operating capabilities of a wind turbine. One is high performance, shutdown on the generator, but then also pitch and yaw control of the turbine to turn out of the wind. And so we can see here our modern wind turbine, the 3-blade upwind design, is really the best in class for all these categories. We see from the efficiency chart at 1, it reaches the closest to the theoretical limit of efficiency of a wind turbine or of wind in general, the Betz limit. And then next to these, it has the ability to mitigate these extreme winds that take place and gradually shut it down, but then also fully shut it down in storm conditions, allowing a lean capex. So every capex of a wind turbine actually contributes to power production. And so a wave energy converter from a systems level perspective, being no different than a wind turbine, really has to meet the same criteria. Next slide, please. Yeah, so as mentioned, we're started out at UC Berkeley. We're supported by a program called Cyclotron Road in the Lawrence Berkeley National Lab. And then our team contested in the US Wave Energy Prize that identified next generation wave technology. And so, yeah, our team did really well there and progressed towards a award we won in 2017 from DOE to deploy an ocean-going unit as a follow-on to being awarded from the US Wave Energy Prize. And yeah, we've now been operating and installing that first system of the Scripps Institution of Oceanography Research here in San Diego. It's been a partner of ours for several years. And then we won additional awards in 2019 towards the deployment at Puckwave, the new 20 megawatt test site in Oregon. Next slide, please. And yeah, so here example on how we really see our holistic control strategy and the architecture that has resulted from that, allowing towards a competitive LCOE with other forms of generation. The first, as mentioned, really has to be high performance, which we've proven and demonstrated in the Wave Energy Prize. And the second then towards the lean capex is the ability to mitigate these extreme loads. And so with our advanced load management mechanisms, we've been able to reduce these loads by an average of factor 2. And that really allows to bring the cost down, avoid the extreme conditions that don't actually contribute to revenue. Next slide, please. Yeah, and here's some details to the project now at Scripps SIO. We've been pre-deploying a local wave data buoy with a partner that's been supporting us with Marine Labs, and getting time resolved data ahead. The site is also really well characterized with a lot of historical data from CDIP that made it attractive. And based on the invitation from SIO for our first demonstration, we've really advanced as the most suitable site, also being in driving distance from us from Oakland in California. Next slide, please. And yeah, here's some first activities pre our deployment in September. And we've deployed our cable about a week ahead of the deployment. We're about a mile out from the pier, and with the Scripps diving team, we've been able to install the cable. Our anchors were already pre-deployed last year. That was possible during COVID, but other operations really had to wait it until normal manufacturing had opened up again. Next slide, please. Yeah, and here's some impressions from our manufacturing earlier this year, then once that opened up again, as well as from the anchor installation the year before. And then next slide. Yeah, and this was then our kind of preparation site at the Mission Bay Marina, probably close to TMA's headquarters. And then we towed from there with the help of the Scripps dive vessel right to the pier, and really was an exciting time for us to get ready for our first deployment. Next slide. And briefly to our SCADA system, as mentioned, we have the cable going back to the pier. We're leveraging an autonomous controller similar to a wind turbine, so our system can continue to operate and shelter in storms independent from cable or grid availability. But then at the same time, we're exporting power and data back to shore, as well as then our advanced controller integrates local weather data for decision making and towards optimum performance, as well as then shutdown in storm conditions. And next slide. Yeah, and next to our DOE-funded project, we've partnered with the Triton Initiative that facilitates the safe growth of the marine energy industry by monitoring And then on the next slide, we see the detailed elements we're working on. So the team from PNNL is deploying hydrophones, as well as other additional sensors that then contribute to the acceptability of marine renewables going forward. And next slide. Yeah, and here we have a brief video from our deployment. As mentioned, we started out in the Driscoll Marina in Mission Bay in September, and it's been really exciting for our team, given the constraints of COVID and delays, still now being able to deploy. And these are some of the impressions from the installation. We can see the vessel from Scripps, so our unit can be installed really with a small and lightweight vessel. The unit itself is modular, so we can ship it in a standard container and then bolt together at site. And so here we can see as we're going out of the jetty in Mission Bay, and then we selected a really friendly day for deployment, and that all went well due to really the detailed planning in advance with the entire team. And here we can see the team installing our unit to our pre-deployed anchors, as well as then connect to the cable. You can see here the connector being closed back to the cable to the pier. And that was then really exciting. The first time we had actual communications control over the unit. And then here's some checkup footage from the divers, just to ensure all the cable connection and everything else has been done according to our plans and standards. And once that was completed, we were able to start operating for installation the devices on the surface. And then for operations, we dive and operate fully submerged. And with that, we're really able to extract energy from all degrees of freedom, get really high efficiency. At the same time, we leverage the water column for survivability. So in storm conditions, we're able to avoid these extreme loads by using the water column for protection, as well as additional mechanisms. We call these active load management mechanisms, where we release pressure on the system, as well as detune it to take it out of resonance from the wave. And with these three independent mechanisms, redundant shutdown mechanisms, we're really able to survive these extreme conditions by not being over-designed, and by then going forward being most economical in CapEx. And on that note, really want to express our gratitude to SIO for the partnership and the entire diving team there from Scripps that have been working with us. It's been really exciting to be able to execute that project now. And of course, the Department of Energy for their continued support to enable us to conduct that work. And with that, excited to jump to some questions.
Great. Thank you, Marcus. Thank you to all the panelists for your presentations. Got a few questions in the chat boxes here, so I'm going to go ahead and get started with those. And I think I've heard a lot of you talk about upcoming ocean tests, Oregon, PacWave, for example. Can you talk to us, and this can go to all of you actually, on the importance of actual marine testing, open ocean testing? I know we have the wave energy test site in Hawaii, which is fairly less of an energetic site than the Oregon site. So what is the value of these high energy sites? How does that help your technology? How does that help investors, utilities, other end users kind of see the end product and potentially move technologies forward? I think, Patrick, you guys have been through EMEC as well, and has that opportunity really opened doors for you? Does that lead into the Portugal project? Are these all kind of stepping stones that without open ocean testing would be harder to achieve?
Absolutely, I can start. I can start commenting then. I think it's critical to have access to open ocean testing. And I think there's some part where you want proof in the local environment. There is, of course, the wave regime in the zone, but there's also the grid connection, and people like to see devices operating in respective regions to be fully convinced that it's sound and viable and so on. So for us, EMEC has been a very important stepping stone. We were using the more protected part of EMEC for a half-scale demonstrator, and now we're working with an exposed site in Portugal. So full access to the worst storm conditions of the Atlantic. So very similar to PackWave. But we also having some clients of us who are considering maybe some PackWave installations also of core power devices as a stepping stone to prove the technology in US waters, even if we have worked already in Portugal. So I think it's very important the work being done there.
Res, go to you if you want to talk about the importance of Oregon. That would be great.
Yeah, so thinking about sort of the other end of the scale from where Patrick is talking about, and for us, the important thing is that ability to demonstrate, to co-develop with partners, integration partners, with customers. So test sites obviously are very important, as Patrick outlined, but it's also the ability to have test sites that are either fully permitted or nearly fully permitted, that allow you to get in and out of the water much quicker than having to start a 2 or 3 year process of permitting a greenfield site on your own. So, in addition to whether it's a grid connection or having infrastructure that's in and around that, for instance, that Marcus was able to enjoy at Scripps, it is that ability to get in and out a little bit quicker than having to do everything on your own. So that for us is a big thing, and the willingness of those partners, say at WETS with the Navy, to allow us to get in there and do some things that are a little bit different in demonstrating assets. It's an important and critical development and set of infrastructure that the DOE, Navy, and European governments have also put in place.
Marcus, go ahead and talk real quick about the Scripps infrastructure as well. I was actually in La Jolla driving through a couple weeks ago and noticed a lot of military action going on about a mile off the pier. I don't know if that's exactly where your buoy was, but maybe talk about interaction with stakeholders at these sites and opportunities to really see how testing and devices may have larger impacts to the larger community. If that's something.
No, certainly. And as the conference is in California, I also want to bring up a site that has been under investigation by PG&E in California, the Wave Connect in Humboldt Bay. And they were really coming from an industrial, end user perspective, more from a developer perspective. They were wave technology agnostic. And then I think they discontinued that larger farm. And one of the reasons they listed is the permitting uncertainty. So I think PackWave as a new kind of first of its kind in the US is really critical. I mean, the first one is always the hardest. And, this was one of the reasons. And if, that one of the top 3 reasons can be outruled by now having avoided or mitigated that permitting uncertainty for future developers for farms, that's extremely valuable and gives confidence then also to the financiers. And so for the Scripps pilot, as mentioned, we're, Scripps is the landowner and been working with us. We had to get local, federal, and state permits. And it took some time to develop these because it was a newly developed site for that specific application. And so I think having that pre-permitted site is extremely valuable for us developers to have that planning security that you can install there and your plans can't get unrailed from certain permitting issues that might come up. So I think that project planning security is extremely valuable as well with a pre-permitted site in place.
Yeah, great. And Jack, not to leave you out of this conversation, I don't know if you guys have done open water demonstrations, but I know you've been doing some simulation work through the Teamer program, and if you could talk about the value of not building to scale early and putting things in the water and utilizing technology and modeling softwares to help move that technology along. It's where we've seen some changes from the Palamises and the earlier technologies that maybe went too big too soon, as like we used to say. So development of new software, new opportunities of expertise. If you could just talk briefly about that and how it's helped you guys.
Yeah, thanks. So just adding to everyone's comments on the utility of PackWave and having these open water demonstrations, we more specifically work with small scale applications and commercial partners that are in the small scale space. So currently we don't need like a grid connected test facility. However, it's tremendously helpful to know that resources is available. So when we actually need to practice deployment with our commercial partners, we know where to go for that. So Teamer has provided us these really great resources to do simulations, and eventually we plan to do tank tests and that sort of stuff. So Teamer provided resources to have these physical workshop space to extend our team's capabilities and skill sets. And I think PackWave is a way to for us to extend the deployment space to kind of serve as a deployment workshop for us to practice with our commercial partners. And also, you alluded to this earlier, Matt, in terms of starting small to go big in terms of wave energy development. I think this is a proven strategy that we have learned from the solar and wind industry. Where they didn't started off by building a wave farm, but they kind of built it on a smaller scale with these solar panels on calculators in the 70s, right? So so we're trying to mimic that strategy, and hopefully that will serve as a solid commercial pathway to move forward.
Perfect, and great segue actually, somewhat of a segue to my next question. How have government policies and decisions and funding mechanisms help provide markets for your technologies? And I'm prompting this question by a lot of the Department of Energy's funding for blue economy applications. Renston, I'm starting to look at you first with that.
Sure.
But feel free to jump in there as well.
Yeah, as I mentioned earlier, co-development is important. When we set out to design the C-Ray after being awarded a FLOA grant 2019, I guess, we spent about 6 months on the road talking to customers. What do you need in a low power system? What's important to you? And the feedback that we were getting was logistics have to be non-complex, needs to be modular, high power to weight, power and data. In the low power market, power really is only half the victory. You have to get data also. And so the importance to us from a federal policy, from a federal funding perspective, is that funding gives us the capability to go out, have those discussions with customers, then come back and make sure that we build the design from the ground up that satisfies those market needs. So I think from an acceleration perspective, from a commercialization perspective, that's a key point, and I think the DOE continues to reinforce this co-development model. In the SBIR topics, the phase 1 release 2 that just came out, co-development is an important part of the marine energy, of the WPTO's marine energy topic. So it's a catalyst. It's critical to. None of us could really get, I think, to where we are today without federal support. So it's critical. Just like the testing infrastructure, it's one of those very important underpinnings of any commercialization program.
I could
comment. Patrick, the European perspective on that would be great.
Yeah, absolutely. And it's great to see how much it's picking up in the US with the support from DOE and others. It's really, really great to see. And in Europe, of course, we've been depending a lot on European funding. And if I take a utility perspective here, when we started out in 2010, 2011, we knew this would be some 10 to 15 years, more than 100 million or so in funding needed. And it's not really a workable proposition to go to VC if you know you're going to follow a structured approach. And I think the learnings after Polaris and Aquamarine and others is very critical to follow this step-by-step approach, prove the performance, prove the viability of both the survivability and the economics of the system in small scale before you start stepping up. And that means you need to work in a very methodic way. It takes time. You cannot really cut corners in that. if you're going to succeed in ocean energy. It's very unforgiving, as we've heard here today. So when you have that kind of plan, the early phases is really more research than commercial activities. So the help from public funding there is absolutely critical. So we actually did incorporate the first 3 stages of stage 1 with small scale tank testing and benchtop testing, stage 2 with a little bit larger scale, and stage 3 with our first ocean deployment, almost entirely using public funding. And then for the first commercial scale single device now, we've involved equity investors. And when you take it that far, then it becomes a very investable proposition. So I think, the private-public partnerships there and the funding is critical to make it work.
Great. Jack and Marcus, feel free to weigh in on that too. And I'm going to prompt a question for the rest of you to think about while you guys are responding to that. What are you most excited about right now? So Marcus, Jack, feel free to answer the first question about government policies, opportunities, funding structures, and if everyone else would like to think about what you're most excited about, we can close out with that.
Yeah, so, just echoing. Yeah. Oh, go ahead, Marcus.
Yeah, just to briefly comment, we're a part of the National Hydro Association as well that advocates for the general marine industry in the US. And they've been really strongly supporting the industry for years now. And I think just recently that really gained momentum. And now with the infrastructure bill, additional funding was allocated to the Water Power Technology Office. And same for us. I mean, the initial program, the Lawrence Berkeley National Lab, was a private-public partnership. And then with the prize being a cash prize, that really helped us to get that initial seed funding to match fund then the larger DOE awards to be able to execute now the open ocean demonstration. So these are extremely critical. And as we've heard about Aquamarine, one paper actually they published while they were still operating was they investigated the funding landscape in Denmark and the UK in the early days of wind, and actually found that I think the UK put more money into wind than Denmark, but dispersed in kind of legislative periods, and as a result, then Denmark really became the leader in the wind industry because they were able to have that continuous carry forward of knowledge and expertise within single entities and not people just leaving the industry because of a 4-year funding gap. So I think that continuity is really critical to bring this industry to viability.
Yeah, and just add to what everyone has been saying, the public funding and the resources from the DOE have given us a tremendous opportunity to engage the end user communities. So through these new funding programs, through the Powering the Blue Economy initiative, there's a tremendous amount of incentive for ocean wave energy developers to speak with the end user communities, so like oceanographers. And on the other hand, the oceanographers really need these critical energy infrastructure to transition to big data. But the oceanographer communities or the ocean observing communities don't really know the wave energy communities, and really they don't have an incentive to speak with the developers. So these public resources and funding really help developers to engage these end users. And I would like to plug in that we have been working with POET and with researchers at PMAC, and we're trying to organize a mini workshop through the UMERC program, the University Marine Energy Research Community, so that we can actually bring these two communities together and get the developers to talk to the end users in a public forum.
Another great way to bring the end users with power producers is to attend TMA Blue Tech. Unfortunately, we can all take advantage of the networking opportunities on the Whova app, but there's nothing like being in person. And obviously, we hope to see you all at OREC in 2022, as well as TMA Blue Tech back in person next year. So we have 2 minutes left. If you guys, we'll start with Marcus this time. Tell me what you're excited about moving forward over the next year, let's say.
No, for us, definitely being able to now execute no more or less restrictions for manufacturing due to COVID. That was really hard for us to be able to, or that we had to wait before we were able to execute this project. And now really excited to process all our data and take these learnings towards the next larger unit, towards PuckWave.
I think Matt got bumped off. Jack, why don't you go next?
Thanks so much. I was just going to say maybe I need to moderate the session now. So the next year is very exciting for us, and we're planning on multiple deployments with our pilot customers, and we're really looking forward to having these big data capabilities for ocean observation. And I'm particularly excited because I'm an end user myself for this type of technology.
That's great. Patrick, why don't you go next?
Yeah, I go next. So yeah, we are extremely excited. We're putting our first commercial scale C4 machine in the water in Portugal. And we got quite a few big project developers now actually engaging in wave energy. We're working with EDP, with Enel, with Simple Blue Energy there. So we're really excited to see the traction happening. And the momentum we're seeing in floating wind at the moment, both in Europe and now in California and Oregon, is amazing. And we hope that we can piggyback on that in the wave sector and see a similar investment boom happening here in wave energy in the years to come. The production profile is really a match made in heaven between floating wind and wave in California and Oregon. And that is extremely exciting, I would say.
Yeah, that's great. And I'll just finish. So I'm going to put my Marine Energy Council co-chair hat on for my answer. For those of you who aren't familiar, Marine Energy Council is the trade association in the U.S. for the industry. But I think what's great is all the kit that's in the water. So Patrick, Marcus, ORPC, Verdant, Motion at EMEC. We have Oscilla that's also in. So it's been great. It's been a huge year. I think it's a turning point for the industry and being able to prove out the promise of wave energy. So I think that for me is, in addition to us getting in the water in the beginning of the year, I think that is one of the most exciting things for me. But in Matt's absence, thanks everyone.
Thanks a lot.